Hello, it's Aslam back here, and I'm going to be going over the first 3 weeks of Calculus 2. Now, there has been so little content, I feel, for Calculus 2 that I didn't even make a week 1. So, I'm going to now go over everything that we've learned so far. So, back in Calculus 1, we learned about basically almost everything to do with single variable calculus. So we learned about the derivative, the definition of derivative, limits, some other miscellaneous stuff. We also learned about the linearization of a function, also learned about integration of a function, applications of the derivative, and applications of the integral. So much more, but right now the core of the concept that I want to go over is the basic idea of calculus, the idea that as you split up into smaller and smaller partitions of a certain thing, that you'll get a more accurate result. For example, with the definition of a derivative, you have some. Let's see, you have a function at a particular point at x, f of x, and then you decide to you add h here, and then you get to you get to another point called x plus h, f of x plus h, and as h goes to 0, you get a more and more accurate representation of the rate of change, and you go from a secant line to a tangent line. Now, I'm not going to go too much more in depth. I just want to kind of recap about what we did. But in Calculus 2, we now are worrying about multivariate functions. And previously, we were worrying about functions which mapped from a real number to a real number. This is single variable multivariate. We're going to be now worrying about functions that map 2 variables to 1 variable. And we now introduce kind of how that looks like. So it looks like this. And here's your function, and here will be your inputs. And you could have your function where z is equal to f of x and y. That's equal to x times sine of y. And this function will not be just on a 2D plane. It will be now in a 3D dimensional space. So a 3-dimensional space, and that's how we visualize our functions. We have this is going to be this coordinate system is going to be a bit different than to electromagnetism, but have a z here, we have an x here, and we have a y here, and we have some sort of input space. So input like region, and that maps to an output surface. Right, and this would be considered the domain, this whole region here, and this this whole z-axis here is going to be considered the range. Now you can definitely go from like n number of variables to r number of variables, and it'll still be the same concept roughly, but it'll be harder to visualize. So we usually stick to 2 to 1, and then once you get to calculus 3, or I think we have advanced calculus, you start talking about vector calculus, or you have Rn to Rn. But that's not what we're going to be doing right now, so we're going to just consider usually just R2 to R. There are multiple ways of visualizing it. So there are, first, let's say, cross sections. So cross sections are when you visualize one plane at a time. So let's say you have Z here, you have X here, right? And your function looks like this in that direction, and then for another plane you have Z here, you have Y here, and it looks like this, right? And then you can kind of create like a 3D map of how it looks like, and you can just make it up to your imagination what it will look like, right? And this is roughly what your function will look like. And this is like a really kind of good way, concrete way of doing this. You can start by setting, let's say, y equals to 0, and that will get you the relation between x and z. And then when you're setting x equal to 0, you'll get the relation between y and z, like a nice single variable graph. Right? So you can use this to visualize it. Another way you can use to visualize such functions is to use something called contour plots. So our contour plots are basically, instead of taking a look at a plane at a time, we're going to look top down onto our function. So let's say we have a function, and we can basically say, okay, if we want to find the kind of like a contour plot, like in a map, you might remember it may look something like this, right? And it kind of shows like the topographical features of, let's say, like a land form or whatnot. And this is quite the same way. And so here you could say, okay, I have z is equal to f of x, y, and then you can set certain values of z. So let's say I want to find the ring around when z is equal to 3. I can take a look down, it'll produce some shape, right? And that will be when z is equal to 3. And then you could do it like for z is equal to 2, right? And then z is equal to 1 in the very middle here. And you would just set your z to be equal to some function. So, sort of an example, let's say you had z is equal to, I'm just trying to think of it. Let's say z is equal to x squared plus y, square root of x squared plus y squared. Then you could say z is equal to this, x squared plus y squared. Square everything, x squared plus y squared, and so you'd have a circle with radius 3. So looking down, this would be your x, this would be your y, and then it would look like this, right? And you have a radius of 3. And this is when z is equal to 3. Alright, and that's the basic premise of a contour plot. Now, this is all fine and good, but now we want to do actual derivatives with our multivariate functions. Now, we can't just use our standard dx with respect to dy anymore, because this only works when you have a variable depend on another variable. Right? And more specifically, a single variable. Right. So instead, we use something, we kind of define a partial derivative to be something in x direct, like, I think it would make more sense if I write it down in math. So let's say if you want to take the derivative, you want to take a derivative in the x direction, right? Because remember, this is a multivariate function. It's going to have both an x and a y. We can't just say, oh, we just want the x and that will account for everything. We also have another independent variable, so we have to account for that. So when you say we have f of x as a derivative in the x direction, this will be equal to f of x plus h y0. I'm just going to give like a kind of notation thing here. Whenever I say like y0 or x0, this means that this is a fixed point. So imagine that this point doesn't even matter. And f of x, y0, and h. Actually, yeah, x0. You can do x0 here. To h, and this will be in the x direction. And if you want to define in the y direction, you can use the limit as h goes to 0 and basically do the exact same thing again. Y0 plus h as y of x0, y0. That'll be h. Okay. And there is a better other notation other than f of fx and fy. You can use also partial f, and so this symbol is pronounced di or d. Actually, not d, because you have df over dx. So di f and di x. So this is the partial derivative of f with respect to x. And then you have partial derivative of f with respect to y. You could also, if you have three-dimensional input, you could also do this, but we're not going to worry about this for now. No, we're not going to worry about three-dimensional input. Alright, so how would we actually compute this? Let's say we have function 3x, sine of 3x plus y. I'm not going to go ahead and visualize this, but we can actually take the derivative of this. So let's say this is f of x, y. Actually, you know what? I'm just going to call it z. So if I wanted to get the partial derivative of z with respect to x, I treat the y as a constant, and I differentiate with respect to x. So sine of 3x, so this will be cosine of 3x plus y, and the derivative of 3x will be 3, and the derivative of y here will be 0, because y is a constant here. So this will be, you could rearrange it, but that's the general idea. With partial derivative with respect to y, so again, we actually have cos of 3x plus y, and then here, so 3x is going to be constant, and we just have 1 on the outside here. Right. You can actually take multiple partial derivatives. You could do you can represent this better with the like the previous notation. So if you had z xx, you would take this again with respect to x. So this would be negative sine 3x plus y, and this one would be 9. So you'll be, you still have the 3 from before, and then you have the 3 again. And if you had zxy, you take this one with respect to x, and actually this one will be negative sine 3x plus y 3. So because this y here will just be 1. And actually, as long as your function is not discontinuous within the neighborhood of where you're taking the derivative, this partial derivative with x and then with respect to y is equal to the partial derivative of z with respect to y and then x. So this generally these are the same. There are some specific circumstances where they aren't, but if you're dealing with continuous functions, then there's nothing really to worry about. You can also compute z, y here, and that will be, actually that will be sine, negative sine, and that will be 3x plus y, just that. Okay? I'll kind of quickly go over this. So it's kind of a review a little bit. Linearization. So you might recall it to be L of x is equal to f of a plus f prime of a x minus a. So basically basically you have a point at a, f of a, right? And you basically take a slope. It's based on slope intercept form, but for a linearization, basically just gives you a line, and then within a very small neighborhood of around a, you can approximate L of x here. In fact, if you are so inclined, if you remember the slope formula, you get y2 minus y1 is equal to x2 minus x1. And if we rearrange some things, we get x2 minus x1 equals y2 minus y1. And you can kind of see where this is going. y2 is equal to y1 plus x2 minus x1. Replace m with the slope of a tangent, right? And replace y1 and x1 with a f of a, and y2 and y2 and x2 with x f of x. And then you get the formula above over here. Just say f of x, whatever. So this is actually kind of quite powerful, and actually later on in the course we kind of expand upon this linearization and go into quadratic approximation, cubic approximation, and then go on and so forth until you get to the Taylor polynomial and go from there. Then this is for a single variable calculus. This is, remember, centered around a point a, f of a. And you can actually extend this to 2 dimensions, multivariate functions. So you could say f of x y is approximately equal to f of x naught y naught. So here x naught and y naught is a fixed point, plus f of x at x naught y naught x naught y naught. So the tangent slope in the x direction, x minus x naught plus f of y x naught y naught. This is going to be y minus y naught. And this will be in the y direction. And this will give you something known as a tangent plane. Alright, if you ever want to find the tangent plane, you can find like amount of values around it. In fact, if you were to take the tangent Tangent plane. Sorry, if you were to take the if you were to take this line and represent it as a vector, you could actually find actually kind of a normal vector to this. That isn't so much important as I would think it to be, but you can think about this if you recall from linear algebra. Maybe you can say, okay, a plane, and that's equal to that. This would be like the point, right, plus m1, right, an m1 vector plus an m2 vector, right, and this would here be the like m1. This here would be the m2, right, and this here would be your point. And you could, if you take the cross product of your m and m1 and you take the cross product of your m2, so if you take the cross product of them together, you can get a normal vector, and that will be like a normal vector to your plane. And you could do some kind of wacky stuff with that. Keep in mind that your m1 and your m2 will be direction vectors here. So, but enough about that. It's kind of like a side thing that you can kind of view as a marriage between calculus and linear algebra. But that's something that you can investigate a little bit more. It's not really too important, but it is kind of something that you can reflect upon. And if you want to, you could go crazy with it, and as I have with calculus and linear algebra together. You could actually, however, simplify this expression over here by expressing it in differential notation. So if instead we had f of x, y, and if we instead took this fx0 of y0 to the other side, then we can get f of x, x0, y0, x minus x0 plus fy x0, y0, y minus y0. You can actually make this into more concrete form. So then we can represent this as delta f, because it's like a change in f from x0 to x0, y0 to x and y. This bad boy can be represented as a change in x, and this guy can be represented as a change in y. So you get delta f is approximately equal to f of x, x0, y0, delta x plus fy, x0, y0, delta y. And if you were instead to kind of shorten everything down, and if you were to now take these differences and make them infinitesimally small, you can now rewrite it as df. So whereas this implies a large change, this represents an infinitesimally small change. It's a really small change. Think of the change of h in regular calculus 1. It's not going to be approximately equal, it's going to be equal to now here, because now it's more exact. It's actually, because it's infinitely small, it's going to be precise. So now instead of this delta x, it's going to be dx plus f of f with respect to y of times dy. Okay? And if you take this, you can actually you can actually kind of expand it out into a multivariate chain rule. Before that, though, I'm just going to quickly touch over parametric curves. And so, usually, when we're talking about a z being dependent on x and y, and and that's all fine and good, but x and y here are independent variables, and it may be kind of hard to think, it's kind of hard to not think of x and y as being dependent on each other when they really are not. So with parametric curves, instead of thinking, actually, the bigger reason though is that x and y, we can take the derivatives, but we don't really have a sense of change overall. But what we can do is use parametric curves. So instead, I can define z to be a function of two variables, x and y, and x and y both depend on t. So we can kind of give that as a kind of vector. Hold on one second. So here, time can be called t can be called the time parameter, because it kind of tells you how time is moving. It's the only variable here that's independent. Both x and y are now dependent on t. So we can actually, z here will actually be a vector. So z actually we use r in this case, but so we can use r is representative of a vector of x and t. So x of t and y of t. And both x of t and y and t they both depend on t, of course. And so we can define x of t to be, let's say, sine of t, and y of t to represent cosine of t. And if we take a t to be, to go from 0 to 2 pi, and we were to sketch out the x and y coordinates for different values of t, you would actually get a perfect circle. You could even change, let's say, sine goes sine of 2t, and it'll actually, what will happen is that y will still go up and down at a regular rate, but it'll go up and down at a regular rate, but x here will now start to kind of freak out and do more cycles, so it will kind of trace a path like this. Right? You can even draw that into Desmos and double check, but this is what this new function would look like, right? And you can see now that x and y are now independent of each other. I can change x without changing y, but it will change the graph. But the most important thing is that it's this time parameter, because this time parameter gives us a sense of how fast this line is moving. With just a regular let's say, like line, and in our multivariate world, or like even just a surface, even like a contour plot or whatever, it won't really it won't really give us a sense of time. So this t variable is very powerful because it gives us that sense of time. Now, and something I just want to mention here, r here is the parametric curve that I'm talking about. So this r vector is a parametric curve, and this is kind of path traced by r. You can kind of imagine r being a vector centered at the origin, and for different values of time, it actually points out here. It's something called a vector valued function, and it actually points out to different directions from this origin. And what the line that I just drew is a representation of those endpoints where they land up at different times, at different times throughout the cycle. Okay, so we can actually describe this instead as not just r, but as a special kind of vector, and it has a special notation. And it's something called the gradient vector. So this is called the gradient vector. This operator here, more specifically, next to a function, and it's acting upon a gradient vector of f, right? So for any function f, if you want to have the gradient vector, or in this case, gradient vector will mean the steepest ascent for any, the direction of steepest ascent. It'll give a vector in that, and I will explain how that works. And then I will go on to multivariate calculus, multivariate chain rule. So the gradient vector here, so if let's say we have f of x, y, right, the gradient vector of f will be equal to, it is related to what I've put up over here, but it's kind of a more, it's hard and stone kind of thing. It'll be equal to the partial derivative of f with respect to x, and the partial derivative of f with respect to y. And this could be extended to n, it doesn't have to be two variables. It could totally be n. But for this sake, we're going to say n is equal to 2, because it's going to make it even more simpler. There is one more thing I want to talk about, and that is something called the directional derivative. So far, we've been talking about derivatives in the direction of y, or in the direction of x, but we've never kind of made a thing where we can have a custom direction where we can measure the derivative, and that's what the directional derivative does. So the directional derivative, you can write it, so you need a vector, so let u be a vector. So I'm going to say it exists in R2. I'm going to be lazy. And you have, let's say you have a function f of x, y. If you want to find the directional derivative of f of x, y, we'll first start with the definition, and then we can go from the notation there. So, actually, I guess I lied. So the directional derivative, you can use this, or you can use this. It doesn't matter, right? It doesn't matter what symbol you use, as long as you're consistent. But they both just mean the same thing. As the limit of h goes to 0, you have f of x plus h u1, or x0, h u1, so u1 is the x coordinate of our vector, y0 plus h u2, so our y coordinate of that 0, minus f of x0, y0. And this will give us the direction of our function in a certain direction. In fact, our gradient vector is actually plays an important role here, because you can actually define the directional derivative as a dot product of the gradient vector, right? So it's actually kind of like confusing. You can, so this directional derivative here, it's saying how much is a change in a direction of a predefined vector, right? But you can write that as the gradient vector dot the original vector itself, and it will always, without fail, give you the direction of steepest ascent. And if, let's say, you were to analyze the dot product, and you say, okay, let's say we have our magnitude of our gradient vector in some direction, and we have u here. Actually, I'm going to use a different vector name because I kind of want to hammer point home. Let s be the vector in the direction of steepest ascent. Right, and you have cosine of theta. Now, what does that mean? Let's say you have your vector s, right? And you have your function, gradient vector, and you have a specific angle between them, right? So f, the magnitude of the gradient vector and the magnitude of the vector itself are going to be fixed. The only thing that's going to be variable is this cosine over here. If we were to draw the graph of cosine, however, 1, -1, and this would be our theta, you'd see that it goes like this, right? You have pi over 2, 0, and 3 pi over 2, right? When the angle is equal to 0, or when the angle is equal to 2 pi, we can see that it's at its maximum. So the gradient vector, I should have probably removed this equal sign, this gradient vector and this vector in this direction of steepest ascent will actually be one and the same, right? Otherwise, then this would mean like this gradient vector will be pointing in the same direction as s, right? And honestly, that is mostly it. You can also just do fx u1 plus fy u2 and continue with however many dimensions you want, or you can do the linear algebra way and just do the dot product that way. But what I want to kind of go over though is the multivariate chain rule. Right, the multivariate chain rule, and this just basically says it's this kind of a rule for when you have multivariate functions. Recall that in your single variable case, right? Let's say you have a function f of x, and actually I'll do it in terms of variable y is equal to f of g of x, right? And then if you do the y derivative, you have f prime of g of x multiplied by g prime of x. And you can remember from actually this is why I wanted to kind of get back to this here. Oh, nope, that's not what I wanted to do. Our linearization, right? We can sort of hand wave this around. So first thing, I'm going to say that let z equal to f. I want z to be a variable here and f be like a separate function. So if you want d of f, we have instead, we're going to now replace with the partial derivative of z with respect to x, dx plus, the partial derivative of z with respect to y, dy. And if you were But now we want to kind of treat our x and our y as terms of like in terms of, let's say, are like a time variable. Like, you remember we had x of t and y of t. We want to do that because then it's kind of useless to have this rule. Not useless, but like, this is the equation of a tangent plane. It's not a train rule by any stretch of the imagination. So if we want to have it with respect to t, this dx is going to be now with respect to t. This df is going to be with respect to t. The reason why I didn't have anything on the bottom here is because df was in respect to both variables, but now we can represent it as a df to dt because we have a single variable for it to depend on. This is sorry, this I messed up. It's gonna be dz over dx, and then this is gonna be dx over dt plus dz over dy over dt. And now you can see that dz is now coupled to dt through some multivariate, through some partial derivatives over here. And oh my goodness, I'm getting thirsty now, but this function, this z, can now be related to t in a single variable through partial derivatives. It's kind of interesting and weird at the same time, but you can do it. You can actually generalize this to more complex functions. So let's say you have z depends on, I'm going to give like the most complex example I have. Say z depends on t, and x, z depends on x, and x depends on s, and it also depends on t. You can write this as, let's say you want to get the partial derivative of z with respect to t. Keep in mind that now that we have more than one variable that we want respect to, we're going to actually use a partial here instead of just a single variable over here. So it's going to be dz with respect to t. First it's going to be this one over here, so it's going to be dz with respect to t over here. I think so. There might be an issue with this one. I'll have to read the course notes again, but you can then do with respect to x, so z with respect to x, and that's with respect, that's x to respect to t. And if you have dz with respect to ds, that'll just be dz with respect to x, and then sorry, I don't have it in my vocabulary yet, but dx, ds. Okay, and this is kind of a more complex chain rule mapping, but keep in mind that it's just keep in mind that it matters whether you are talking about a single variable function or multivariable function. Usually you're going to be doing multivariable functions, so you don't really need to do, you're not going to really see dz over dt, but it's something you have to keep on the lookout for. Otherwise, that's basically everything for Calculus 2 for the first 3 weeks, which is kind of why I put off doing this video, because it was so little content. It's just, oh well. Anyways, and that will be it for now. I will see you later.